you have to get over to this little speaker icon.
Oh, I can see everyone. Okay, I do have a request. So as you all know, that it's not as exciting presenting things online comparing to in person. Uh, if you can turn your video on, I would really appreciate it. Because basically, that's gonna really change the quality of my presentation. Thank you. And even if you turn it on and halfway you have to turn it off to do something, I'm completely fine. As long as I can see like 2 or 3 or 4 or 5 happy faces, that keeps my morale high, and you do get a better talk from me. That just, I know how I function. So my energy level will drop if I don't see any faces. Thank you so much for doing it, and thanks a lot for Wolfgang to actually organizing this conference and putting everything together. I can't imagine the amount of hard work you have to put without the actual the sort of benefit of being able to meet everyone in person, going for conference dinners. These are kind of the things that's really nice from conference. But Wolfgang, thanks a lot for putting everything together, because I think this area you're working on, AI and VR, is a very important area. We have such a nice community today, and from the past 2 conferences I've been as well. So a big thank you to you. And without further ado, I'm going to, wow, thank you for doing your video camera. It's fantastic. I'm so happy to see so many faces. Okay, so today, and the reason why I think it's really important to turn your video on everything is because my research area is social interaction, right? So I know that how much sort of social facilitation, audience effect speakers will get from their talk. So it's backed by research, not just me wanting to, see faces. It's actually quite common. Anyway, so I am a professor in virtual reality, and I have been doing VR for quite many years. And today I want to probably focus on talking about applications in 3 areas I have been working in: social interaction, using social interaction in training, and the work I've been doing with neuroscience research, and also finally this work we've done with game companies on creating AI characters for immersive gaming. Okay, and before I start, I'm going to ask you a question. Which one do you think is longer? Right. Sorry? You can't see my slide? Oh, have I not? Oh, sorry. I didn't realize. Yeah, that's a small detail that I forgot to share my screen. Here you go. Well, thanks for saying that. So I'm probably just going to quickly go back and show you the previous slides. Right. So these are basically the areas I'll be talking about today. So before going there, I have one question for you. Which one do you think is longer? The one on the left, or the one on the right? Just shout out. Left, yes. Okay, so I'm just now going to play the video. So this is a home recording during my time when I was on maternity leave. And I think this is a kind of IKEA train track you can just get. So as you probably know, that despite knowing that these 2 pieces are exactly the same, they're identical, we can't stop thinking that the one on the left is longer, right? Hopefully you'll agree with me on that. So this is called an illusion. And for me, the reason why I mention this is because I believe VR is just an illusion, but supported by technology. Basically, through real-time tracking and graphics, VR is able to tap into our interface with reality, and by replacing the world around us with simulations, they can trigger illusions which could challenge and reshape our beliefs of the world we live in. And this is not the only example, just to show you a bit more examples, not only just me discovered visual illusion, right? So in the first image, those horizontal lines are actually parallel. Yeah. And then in the second image, if you kind of look away, sometimes the image looks like as if it's moving, but it's not. It's actually just a static image. And then on the third one, you're just going to have to take my word for it. So the square labeled A and B are actually exactly the same color, the same grayscale, right? Don't try it now, but later on you can do a screen grab of this image, or just Google visual illusion, and you can use the color picker to see it. It's a bit mind blowing, but you're just going to have to take my word for it for now, right? So hopefully all these I demonstrated to you that our interface with the reality we're in now is not as reliable and robust as we like it to, as we think it is, right? And as I said, for me, the reason why I'm mentioning all these illusions is I believe VR is just an illusion like this one, but in this case, it's supported by technology. And I'll explain how VR actually works. So as I said, VR for me is an illusion. And technically, this is how it works. When you put a VR, have you all tried VR headsets, everybody? Yeah? Okay, brilliant. So you must know kind of the magical feeling when you put a headset on, you all of a sudden feel you're somewhere else, right? But actually, that's just technology. So you put a VR headset on, you see 3D vision because you have one separate image for each eye. That's how we see 3D, okay? And then secondly, surrounding. You literally have it, in your face. You can't escape, right? So in a way that in VR, we're trapped inside virtual reality. Just like when you take the headset down, we're actually somehow trapped in reality. Okay? Does it make sense? And then thirdly, and also importantly, VR supports something called sensory motor contingency, right? So I mean, here I'm talking to a flat screen, that's why it's not as exciting, and that's why I really have to see your faces. But in real life, I get a bit more energy because as I move around, I see people in front of me, and as I move, my brain automatically integrates the visual input I receive with the motor movement the brain detects, right? And the brain automatically integrates these two signals it receives, and that's how we develop our perception of reality. And this is very important. This happens at a subconscious level. We don't have to think about it, but that's just how we develop our perception of reality. And in VR, thanks to the kind of tracker we have inside a headset, that's a built-in tracker, tracks 6 degrees of freedom movement of our head. And then that tracker works very quickly. And also the information is then used to update the graphics display we see inside VR, and everything will happen within 10 milliseconds or so. And that's why we're able to see virtual displays updating with something like 60 to 90 hertz frame rate. And that's how we kind of develop this vision, this illusion of whatever we see in VR is actually real. Okay, so this is basically when sensory continuously opens together with the fact we're kind of trapped in VR, together with the fact we see things in 3D. We really have this strong illusion we're actually somewhere else rather than where we physically are, right? So that's how VR works. So inside VR, we have this strong sense that we're somewhere else, and there's another image showing that illusion. So he is, obviously immersed in the headset, slashing cubes. However, he does seem a bit mad in reality, right? But because he doesn't care about reality, for him, all it matters are these cubes flying towards him. And also kind of relevant area that I work in, not only VR takes you somewhere else, but importantly, it can also take you to be with somebody else. And that's kind of the area of social interaction VR I have been working on. So this is one of the very first VR application I implemented back in 2005 when I was doing my master's degree at UCL. And we had the cave-like system. So at that time, we do have headsets, but they're really quite heavy. I probably can sort of wear a headset for about 5 minutes before my neck breaks. So in this case, we did the experiment in the cave-like system. So the participant would wear a pair of shattered glasses. So you have the sort of the glasses blocking one eye at a time. That's how you see 3D, and it's all synced to the projector. And also he's wearing the shattered glasses at the tracking system. So as he moves his body, the display updates. So cave-like system are actually single user system. Although if you stand next to him, you have a bit of sense of how the experience is, but the truly immersive experience only happens to the person who wears the glasses, because all the displays are actually updated towards his perspective angle, right? And it's also surrounding, because you not only have the 3 walls back projected, you have the floor front projected. So you really feel that you're inside that virtual space. Okay, so I'm just gonna show this video. It has a little audio as well, which might not work too well, but let's see.
That shirt looks great on you. How much was it? I think it was about £20. It's quite cheap. Thank you very much, though. You look very nice too.
So as you can probably see,
Thank you very much.
He's wiggling his body. He's definitely enjoying this conversation, and he's enjoying this conversation so much, he actually went all the way to the back wall of the cave-like system in order to be closer to her. But what he didn't realize is that we actually programmed the avatar to maintain an interpersonal distance away from him. So the more he pushed forward, the more she actually stepped back, right? And then he's trying to be so close. He went all the way to the back wall. But this really indicates that he's really enjoying the social interaction. And that's exactly what we were trying to achieve in this work, because we want to create a place where people who are otherwise struggling with social interaction can actually practice with virtual humans. So this way they can build their confidence with those virtual characters until they're ready to embrace the real world. And that's basically the story of how I got into virtual reality back in 2005. Okay, and moving forward. So since then, that has always been kind of the theme of my work, which is to use the magic of VR to really improve how we socially connect and communicate with each other. And as we all know, the mind is very complex, and during social interaction, it gets even more complicated. We connect with each other by exchanging different social signals when we interact. You know, it can be voice, tone of voice, gestures, facial expressions, lots of things. So the process is very complex, and very often it gets overwhelming, and it's even mysterious because a lot of those social signal processing and exchanging actually happens at a subconscious level. But hopefully we all had a sort of magical moment, you know, when two minds really connect perfectly with each other. Is a great feeling, right? I mean, I hope you all had the privilege to have worked with someone who, you know, are operating at the same wavelengths, we say, right? So I hope you will understand that together you can achieve a lot more than, you know, than on your own. But that is not always the case. And actually, in real life, very often we'll have two very different minds having to communicate something. And that's make communication between these two people very tricky. One example could be when a medical doctor tried to explain a treatment plan to a patient, right? In this case, not only the medical doctor is way more knowledgeable than the patient, and the patient knows very little about it, but also in terms of priority, this is very low priority for the medical doctor because they're probably going to see 20 patients every day. They just want to see you, explain to you what it is, and move on, right? But for the patient, that's probably the only thing they care about for months or even years, right? So when this kind of thing happens, the communication could get a bit tricky. Or even worse situation could be that, you know, someone may have a really sort of fully functioning mind, but they have a defective interface in the way they socialize with each other. For instance, someone who suffers from social anxiety, or people suffer from autism, or sometimes people suffer from depression. You have different, you know, you kind of social function is actually broken. So the key of excuse me, the key of my work is that I believe VR could be a potential solution to lots of the problem we're having in social interaction. And basically, there are three kind of complementary and iterative steps I've been using to tackle these problems. So first, I try to use VR to provide a realistic, safe, repeatable, and controlled environment for practice, training, or therapy. And then secondly, we can use this virtual environment created as a tool to actually help neuroscientists to study the brain mechanism behind social interaction. Because as I said, a lot of the things we use in social interaction is very complex and even mysterious. So we don't really fully understand social interaction in real life. But using the tool of VR, we can actually help advance in this area. And last but not least, we can use the insight learned from these two steps to then develop more effective VR and feeding back into this loop. So today I'm going to try to present one or two studies out of each of these three steps. First, let's start with social interaction. First, let's start with social interaction training. Okay, so I have two examples. I probably will go through probably just the first one because otherwise we'll run out of time. So I've been doing lots of work on doctor-patient communication training. And I want to give you an example of where we collaborated with medical doctors on antibiotics prescription. So just a bit of background. So I don't know how much you know about superbugs. Basically, superbugs are antibiotics resistant bugs. So this is the kind of thing, basically medical doctors, modern medicine doesn't really have any means to help people who are basically suffering from superbugs. And one of the main contributor of superbugs is actually the overuse of antibiotics, right? So if someone doesn't need antibiotics, but then they had access to it, then it increases the likelihood of some superbug will actually generating different kinds of superbugs, basically. So as medical doctors, they all have the responsibility to try to safeguard antibiotics prescription. They can't just like anyone who come and ask for antibiotics, they just give them. They have to make their best judgment and only reserve the antibiotics to those who actually need it, right? So if you don't do anything, basically by 2050, about 10 million people will die because of antibiotics, because of superbugs. So this is actually quite an important area of work. I'm gonna just play a video of what we've done in VR. So I just want to mention, in this case, you have a medical doctor sitting with a headset on, and he sees two virtual patients. Actually, one of them is virtual patients, this elderly woman who has a cough, who wanted antibiotics, and she came with her daughter, who just, very angry and arguing for antibiotics all the time. So that's what we've done, but I'm gonna show a video as well.
Isn't it better that we give her some antibiotics to help her immune system.
Well, unfortunately, that's not how antibiotics work.
Be assuring as I can, I do not think that there
This
is...
is so unfair. It's going to ruin our holiday. I'm going to take this up with the local health authority. I think you are unfairly denying medicine to my mother.
Okay, I appreciate your concern. Thank you for your feedback.
My mother worked and paid national health insurance all her life. Now look at what's happening.
Sure, I mean, this has got in no way to do with your mother's health insurance payments.
They say on the news that old people are just invisible, not treated with respect by the NHS.
Thank you very much for
I
sharing.
suppose that this is all government cuts to the NHS, but that's just an excuse. You could give us the antibiotics if you wanted to.
Well, I don't think it would be good clinical medicine, as I've explained before. I'm very sorry to have to cut the conversation.
Okay, so basically we ran this study with 21 medical doctors, and I think 12 of them are fully trained medical doctors, 9 of them are trainees. So in the UK, you can sort of finish your training, but then you're still a trainee until you have maybe 3 or 5 years of experience. So 9 of them are actually trainees, which means that they're still practicing medical doctors, but they're just not as experienced. So we give them this scenario, and they know that this is a clear medical case of where antibiotics should not be prescribed. And they know that these patients are not even real, they're virtual patients. And they understand very clearly that, okay, this is a typical scenario. We shouldn't prescribe antibiotics, and they're being videotaped for what they do. But still, guess out of the 21, how many of them actually gave in? Just gonna show the result. So basically, 4 out of the experienced GP managed to say no towards the end, and none of the trainee GPs managed to say no, right? So it's quite a surprising result for ourselves as well. And I'm just going to show you some comments. It felt stressful as I felt the character were putting me under pressure to make a decision to prescribe. Really useful for testing how you respond to difficult situations. So basically, we presented with lots of conferences with medical doctors in the UK, and I actually took this to the Whitehall with politicians, showed them to the politicians, and I remember really interesting. When we were setting this up, we were waiting for the politicians. A couple of interns kind of tried it, and normally within like 3 sentences, they're like, "Okay, here's your antibiotics. Just leave. I can't argue with you anymore. It's too stressful." Right? And then we had a very experienced politician. He must be someone quite well known. I didn't know who he was at the time, so he put a headset on, and he was really arguing with our virtual characters, right? And then to the extent that his assistant was sitting next to him, and he was like, "Oh, you're late for your next meeting." And he's like, no, let me finish my argument. This is important. We found it quite funny. We found it like, he's not even a medical doctor, so he doesn't even know how to argue, but he's just so good at arguing, right? So I think this kind of scenario is really something you do gain experience and confidence through practice, right? So I really see kind of the point of using VR to really help him to go through the practice, so that when they are confronted with real situations, they don't make the same mistake. And then because of the success of that work, we also done other work in terms of child safeguarding concerns. I don't think I have the time to show it, but I just want to quickly show that we did kind of created child abuse cues with professionals. And this is really the critical message we want to send in this area of work. I'm just going to quickly show you this video.
He'll be quiet, right, Tom? Tom, sit here. I don't know what's going on in this boy's head.
Right, so we implement these cues, which I think even for everyone here is quite obvious that the father was, being quite abusive to the child. And these are basically suggested by Professor Caroline Furterman, who is a consultant pediatrician, but also one of the co-authors of the Child Protection Practice Manual in the UK, right? So we're really privileged we were able to work with her, really develop this scenario. But I don't have time to actually go through what we've done. I just want to say that in this case, we actually did our experiment in the K-VAC system. It was because with the antibiotic scenario, some of the medical doctors complained that they didn't have access to a computer, because I don't know in other countries, but in the UK, when you go to the doctor, 80% of the time they're staring at a computer screen. They barely even look at you, right? Because they want to look at your medical record, and even only when they ask you questions, they look at you for a second and then they go back to their computer screen. So we had medical doctors complaining that the situation didn't feel realistic because they didn't have access to a computer screen. And then in order to try to solve that, because even now I think it's very difficult to set up a virtual computer inside of VR. It's not entirely impossible with the resolution we have now, but it's going to be quite tricky. And back doing that work, it was done in 2017, 2018. We absolutely didn't have the HMDs that would support the resolution that would enable anyone to have access to a computer screen. So we actually conducted experiment in the cave-like system where the medical doctors can have a screens, because with the glasses, not only they see virtual reality, they also see through and see a computer screen in front of them. So that in this case, they were able to type some notes as kind of they always do in real life consultations. They would type up the notes, and we use the notes as our dependent variable for our data analysis. And we had some really interesting results, but I don't have time to go through. So I just want to also very quickly show you some of other work we have been doing in this area, just to show you the kind of graphical and animation realism we're able to achieve. And this is the work we're collaborating with GOSH, which is the Great Ormond Street Hospital in the UK. It's the biggest children's hospital in the UK. And this is about having difficult conversations with parents.
This is happening today. I am not going home today. Now, I don't care about the other patients. I'm sorry, I just care about my son. Are you saying that my child is not a priority?
Okay, so this is the kind of animation we were able to do with a professional actress, with our own motion capture system in the lab. We also did facial motion capture as well. And I have another similar one, which we did 2-person motion capture. This is in collaboration with Zurich University of Applied Sciences, where we're trying to understand the psychological impact of domestic violence on children.
I mean, look at the state of the place. It's a mess. And I'm supposed to give you money. For what? So you can have fun with your friends while I work hard to earn money and no free time at all so that we can make ends meet?
That's untrue. You're not being fair. I look after the household and our child all day. And just yesterday, I vacuumed the whole apartment and I tidied up. You just don't see it because you're gone all day.
That's enough. You shut that.
Okay, I cut the swear word out. Yeah, so that's just to show you the kind of, I don't have data on this work yet because it's still ongoing, but just to show you the kind of quality of an animation we're working on. And we're really privileged to benefit from working with professional actors. And that's really, really important in creating this kind of scenario. Right, so that's the work I've been doing on social interaction and training. I have also been working with neuroscientists on social neuroscience research. So I'm just going to give you one example of work we've done in this area. So a bit of background. So I was working at SEN, Institute of Cognitive Neuroscience at UCL for a couple of years. And my PI at the time was Professor Antonia Hamilton. She is professor in social neuroscience. And they were very interested in using VR. And that was back in 2013. And at that time, we did have some headset, but it wasn't really, the graphic resolution wasn't great. So instead, we used this kind of system where we had participants sitting behind a desk, and in front of them, they have a big projection system. So it's almost like they're sitting in a desk, and opposite to them, there's another person sitting, right? So we kind of have that kind of, you say that can be called maybe semi-immersive virtual environment or extended reality or mixed reality, however you want to call it. But we also put 2 magnetic trackers on the participant, one on their head, the other one on their fingers. So we can track the way they move their hand. That's kind of what we measure. But we also track their head so that when they move around, the virtual character is programmed to be interactive. So the virtual character can be kind of looking at them. Right, so that's kind of the technical setup we have for this work. And before going into the actual work, I'm going to do a little interactive experience. So if you can all do this with your hand, okay, just copy this, okay. So when you see the next image, open your hand as soon as possible. As soon as you see the next image, open your hand, okay? Okay, let's try to do it again. Okay, very good. And now you are going to do the same thing. As soon as you see the next image, open your hand, okay? Very good. Okay, good. As you can probably feel that the second one is slightly trickier, right? Because the first one is a congruent condition, right? You are told to do exactly what you see, where the second one is an incongruent condition, where you're going to do something different than what you see, right? In particular, this one is the image of a human hand, which we all react to very strongly, subconsciously, right? So basically, this experiment was first done in 2004 by Cecilia Hayes, and has been repeated many over and over again. We always find a really robust mimicry effect, which is that our reaction time is smaller, so we react quicker with the congruent condition compared to the incongruent condition. And this is after training effect. You can, get people to train, but then you will still see the difference here, right? So this is just, how our brain works, the mirror neuron and everything. And it's actually summarized by Barha and Chatterand as the unbearable automaticity of being. So there's part of, things that are happening in our brain that are just out of our control, that, just actually drives how we interact with each other and with the world. And that's quite, fascinating. At the same time, how to say, there's not really good way to study it, right? Because we don't even know what it is. We don't even know how, we can't even predict our behavior. We don't even know what is it we're trying to test. But that is also important. It's just not about finding something fascinating, because there are brain models out there that neuroscientists are trying to use to explain neurological disorders, right? Because the neurological disorders, a lot of them is about certain functions we all share, but maybe certain people have some problems in this function, therefore they behave slightly differently from us, right? Therefore, it's actually important to understand how the brain mechanism behind those automatic brain functions. And this is a model proposed by Antonia Hamilton back in 2008. So she proposed that we all have the tendency to mimic each other, which is the implicit and automatic copying of the detailed kinematic features of an observed action, rather than just the action goal, right? And this kind of in the brain goes to this lower pathway. So we see something, and then we have the tendency to copy that with our motor part of the brain, right? And then that then drives the motor output. But there's another pathway as well, which is emulation, where we copy the explicit goal of an observed action. So we'll see an action, right? And then we'll try to interpret at a higher part of our brain to interpret what is the goal of this action. And then we'll also have the tendency to have to copy this goal, and that drives our motor action, right? So lots of the times, let me just give you an example. So for instance, in a conference, if I see someone, grab a glass of water and start drinking, I might do the same, right? And in this case, my mimicry tendency is to have my hands out, and then I start thinking, oh, this person's drinking water and it's good to keep hydrated, so I'll drink water as well. So in this case, the mimicry and emulation function kind of agree with each other, therefore I conduct this action, right? But if I go to maybe a party, I see someone grabbing, getting a can of Coke from the place, then I might have my hands out, and I think, oh, actually, I'm trying to, be healthy. I don't want to drink Coke, so I take my hands out, right? So it's like in this way, the mimicry sort of pathway is still there, but when the goal is interpreted, I decided not to take the action, so I take my hand out, right? So basically, there's a mimicry, which is quicker, and there's an emulation, which is normally slower. But in most of us, these two pathways kind of act together to drive our everyday interaction. And the hypothesis here is that people with autism, they might have some abnormality in this mimicry pathway. They might have this pathway not as strong as everybody else, right? So in order to test this theory, we recorded one of the students in the lab basically help us to record this. So get this student to sit in front of a desk. We had, say, 4 red dots in front of her, labeled as 1, 2, 3, 4. And we get her to touch the 4 dots, but we get her to do, they say, 3 at a time. Say 1, 2, 3, and then she can do 1, 2, 4, and then she can do 1, 3, 4. Okay. However, we get her to do each combination at least twice, right? So she can do 1, 2, 3, or she can do 1, 2, 3, right? So she does it either with a low trajectory or a high trajectory. Okay. And then we, have all this data, applied it on a virtual character, so we can actually randomize the order of those animations. And then we invited both neurotypical participants and people with autism to our lab to basically, interact with this avatar. So we told them that, look, just if the avatar does 1, 2, 3, you also do 1, 2, 3. That's all the instruction we give them. We don't tell them to copy the trajectory, of course, right? But when we look at our data, our hypothesis is that the trajectory of the avatar will actually have an implicit influence on people's reaction. And is that right? Okay, so that's the result. So first, let's look at NT, which is neurotypical participant. And in their case, when they have the avatar doing the high trajectory, their peak height on average is also higher comparing to when the avatar is doing the low trajectory. You can see my mouse, right? Can you see my mouse? Yeah, good, right? So you can see there's a big difference for neurotypical participants. And that is also true for ASC, where their trajectory is, their peak height is higher when they see the avatar doing kind of the higher trajectory. However, the difference is a lot smaller. So there's an interaction effect as well. So basically, in both groups, there is evidence for mimicry. However, we did find evidence that people with autism mimics less in this case. Okay. So that's all good, but we had another hypothesis which didn't work. So we also implemented actually 2 kinds of avatars. One avatar is socially engaged with you. And as I said, participants all wear a tracker on their head. So the avatar is able to actually just look at you, really staring at you during the social interaction. We also had a disengaged avatar who would look away when you do the task, right? So our hypothesis here is that this kind of social engagement would facilitate this mimicry effect. So when the avatar is looking at you, you're even more likely to copy her. Is that right? Nope. So that's not what we found. We actually didn't find any evidence. So if what I said is true, then especially at least with neurotypical participant, this high minus low should be bigger. The difference should be bigger with the engaged avatar compared to the disengaged avatar. But that is not the case. It's actually slightly the other way, but it's not statistically significant. And neither is the case for people with autism. And we think that could be, a few reasons why this happened. First of all, our setup is not exactly VR, right? So, so it's not actually fully immersive. And secondly, we think maybe when the avatar is looking at you, she's just looking at you. She's not actually engaging with you because she's not reacting to you, right? There might be other things you do. You either did the task really nicely or you made a mistake. And when you made a mistake, you did it nicely. She doesn't have any other reaction programmed in her, right? So I think maybe that was the reason the engaged avatar wasn't actually as engaged as we were hoping her to be. She's actually more creepy than engaged, and that might have changed the result of our finding. Oh, yeah,
anymore.
okay, I see.
Maybe that has to do with it.
Yeah. Oh, yeah. That's what happened. I must have pressed the key by mistake. Sorry about that. Just step out of the stadium virtually. Okay, cool. So that's kind of the second piece of work. Now it's all good, right? You can all hear me and stuff. Okay, cool. Right. So yeah. So that's kind of the work we've done with social neuroscience research. And as I said, we feel the avatar might not be actually engaging with you. And that could be one of the problems why our second hypothesis didn't quite work. And that actually then led to kind of my third piece of work, which is about creating more effective VR. And in this case, we're trying to basically using AI, and that's probably why my work is related to this conference, AI AIVR, right? So we're trying to use AI to create more effective VR. And that's the example I'm going to show you as the last piece of example. And how much time do I have? Yeah, I'm going to try to wrap this up in the next 10 minutes so we can leave 10 minutes for questions. Okay, so right, so we have also been working with neuroscientists and also the game industry on developing more effective VR by programming actually responsive virtual humans. And some of the work we've done is really about understanding a bit more, collecting data from real life social interaction, because as I said, we don't actually understand real life social interaction. It's actually really difficult to study. So we had like pairs, dyads of participants interacting with each other. We try to capture as many social signals as possible, and see if we can use machine learning to try to predict, to try to train some models to predict their turn taking or eye gaze behavior and stuff like that. But we also had the privilege to work with the creative industry based in London on creating AI characters for immersive gaming. And in this case, we're actually working with the company who did a VR game for Peaky Blinders. Do you all know Peaky Blinders? Have you heard about this? Okay, good. Whoever is nodding, consider yourself British, because that's almost like my test question of how British you are, right? So it's like this thing that's really popular in the UK, but people outside the UK who don't care about British culture just really never heard of it. But it's quite a fascinating TV series, I have to say. It has really strong characters, and that's why we think that was one of the reasons we think it's very interesting to work with them on creating AI characters for the immersive gaming they're developing. So this work was founded by Innovate UK, and there were 2 game companies involved, Maze Theory and Dream Reality Interactive. And Russ Harding is the creative director of Maze Theory. I actually played some of his early games. He used to work for Sony Studios, London, and then I think the London Heist was produced by him. It was 2000, maybe 13 or 14 when I tried an experience where I had this character who gave me a cigarette, and I just broke in and the cigarette got lit up, and I was like, wow, this person really understands immersive experience design. And that was basically Russ was the creative director at the time. So it was a privilege to work with this team, definitely. Right. So basically, we basically trying to develop non-player characters and try to use AI to drive them, right? And if you don't know non-player characters, NPC, they're just, in gaming, you have avatars, which represents another person, another player, but you also have non-player characters when you're playing offline. They're just, creatures who are populated in the game who, have some kind of narratives behind them. And most of the time, the way we interact with those non-player characters in gaming is through something called explicit interaction. Majority of the time, actually, you go in and kill them, right? You shoot them and they're dead. That's kind of the most gameplay, unfortunately. But a lot of times, there are lots of narrative games, you also get to have a conversation with them. But in this case, most of the time, the character will say something, and then you are then provided with 3 choices, and you have to choose which one you want to go with. And for me, this kind of breaks the whole point of VR, because VR is an illusion. You have the illusion you're really interacting with someone, and then you're then told to choose one of the answers, and that for me is just that nothing feels kind of immersive or real or plausible anymore, right? So, and then the Peaky Blinders team we're working with, they're also, they really felt the richness of the character they have in this creative piece they created is really the sort of the signature of what they do. So they want to explore the richness of their character in order to engage with the player, right? So they want to make the player really part of the interaction, right? So it's okay, great, we can do something amazing together. And they were like, also, by the way, players in games, they don't make them talk to virtual characters. We can't take that risk because this is a commercial game. We don't have evidence players would talk to non-player characters. We can't take the risk of actually designing something involving the player talking. I was like, okay, great, what do we do? So we had lots of sessions with sticky notes, and it was really great to actually have it as a funded research project, because it's not really all smooth sailing working with game designers. Although they do very similar work to us, but the way they think, their priorities and everything is actually very, very different. And we also have other constraints as well, because it's a commercial game, we're going to have to publish. So it has to work on existing VR HMDs, which means that we're limited in the computational power, and also we're limited to whatever the headset data can track. So we don't have any access to any of the fancy tracking we normally do in affective computing. Okay, so where am I? So we decided then, after many sessions, to use something called implicit social interaction. So here we want to use the body language we captured using the VR headset as a way for the player to gain trust from the virtual character. Okay, so I'm going to explain what it is. Actually, I'm going to play 2 videos and ask you which one of these 2 participants you think is more socially engaging with the character.
Under the trees, scattering the little things. But she never told me off. Instead, she'd pat the grass and we'd sit snuggled up, waiting quietly for the birds to resettle. They always did. And then she'd say, "See, no harm done." And she was always right. Their darting black eyes as they tweeted unknowable messages to, I guess,
Okay.
under the
then
trees.
The second one.
You're looking for somewhere else to call home. I often imagine them happy in some other park, but the image doesn't come naturally to my mind, so it can't be true. I feel sorry for the finches, don't you? He didn't seem to care about us much. I used to think I could make him if I loved him enough for both of us. But guess what? It didn't work. It didn't change a thing yet. And when she died...
Okay, so which one do you think is more engaging, the two participants? The second one, okay. I hope you all agree. And which one, if you were the virtual character, which one would you trust? The second one, right? So that's exactly what we hope as well. So yeah, so we want to here use social engagement as a game mechanic. So participants come in, you know, if they actually display, they're really listening to the character, then the character will reveal a secret in the end, right? So that's kind of a game mechanic. But here I just want to summarize this concept of social engagement, because the judgment of social engagement, I think in this case, these two people, they're quite clear cut, right? The first one is not as engaged as the second one. But when you're making a judgment, I hope you will agree that it's actually based on quite complex behavior. We all make this judgment, right? And if I ask you, why do you think the second one is more engaged? I'm sure you will all give all sorts of answers, but you know, you'll give different answers as well. So it could be quite subtle and subconscious how we make the judgment. And we might, in this case, it's quite clear cut, but in some other cases, quite arbitrary. So we might actually have different judgment over the same situation. And in our game design, we want to make sure the person who actually make the judgment is Russ, is their creative director, right? So we want to make sure the game is designed in a way that he feels that he's in charge. It's almost like the hope is that he is actually in the living room of the player to make the judgment when the player is playing it, right? So we want to make sure that we take his judgment here. And also, as you probably all know, because most of us doing machine learning, we're going to train a machine learning algorithm to be able to label the data from the data Rust labeled. We're able to then use the machine learning model to make the automatic judgment. But here, we don't want him to make the judgment with a video feed we saw, because for the machine learning model in real time, they won't have access to that video, right? We can't get a camera into the player's house. But instead, the kind of data the machine learning model will have is actually just whatever we're able to record in VR, right? So here, in order to label the data, we get Ross to put a headset on, and then we play the recording of the interaction inside VR, and for him to make the judgment that way, right? So this is kind of, you know, one of the innovative point we have for this work. And yeah, just to kind of recap it. So we have the player who has basically the headset and the controllers. We have kind of 3 of the 6 degree of freedom data points. And then you also have the VR scene data where the avatar is doing and everything. And then we get Rust to review it and label whether the user is engaged or not through the VR headset. And then we feed those data into the machine learning model so that the machine learning model then learns how Rust will make the choices, right? And then when we have a new player, the machine learning model will be able to output in real time whether they think the user is engaged or not. And then we can use this information to update the game in real time for the character to decide whether to reveal a secret in the end or not. So that's kind of the whole design of this work. But in our case, we wanted Ross to be the one labeling everything. But guess what? When we were at that stage, they're also doing the VR game of Doctor Who. So they didn't have, Ross was like so busy. There was no way he's going to sit with us for a few hours to do the labeling. So our PhD student, Christina, has to be the one who did the labeling. But that doesn't matter because we're just testing the pipeline of whether the method we create works or not. So I have another video which explains a bit more of how this works.
We can understand how humans interact with each other and can say, from their body language, whether they are socially engaged or not. In virtual reality settings, this helps maintain plausibility illusion, but it's difficult to implement, as our judgments are subconscious, so we cannot come up with a set of explicit rules. In this work, we collaborated with 2 game studios and developed an immersive machine learning pipeline for detecting these kinds of human-defined social attitudes in VR games. First, Volunteers took part in a social interaction with a virtual character. Next, an expert annotated the social interaction in the same immersive medium. This data was then used to train a machine learning model. We considered different model configurations, out of which the one that is pre-trained and with a temporal memory performed the best. In terms of input data, we trained it on raw features, such as head position, as well as psychologically based features, such as the distance between the user and the character. The model using the raw features could not generalize to different virtual character positions, whilst derived data performed with 83% accuracy. This work contributes to the field of socially responsive virtual characters, offering a design by example tool for immersive machine learning to detect abstract social attitudes in VR social interactions, and allowing future VR games to be more engaging, immersive, and inclusive.
Okay, right. So just also want to emphasize the pipeline we have created can also be generalized to use. In this case, we used social engagement as the social attitude we're detecting, but we can easily use the same concept for other social attitudes such as sympathy, affection, or aggression. So just that in the labeling process, instead of engagement, we can get the VR interaction designer to label something else. And yeah, so I think this is really interesting piece of work. I just want to say it's like quite rare you have the opportunity to have to work with the industry. And in this case, we learned a lot from each other. I just want to have a quick summary, right? I feel that in current games, characters are often not aware of what the player is doing, and that kind of a lot of the times, when you enter in a place, when the character is talking, a lot of times you just like randomly exploring the room or even throw things at a character, right? So it's almost like a way to kind of encourage people to be quite aggressive towards maybe not another human being, but a human-like virtual agent, right? So that on its own, it's quite a strange idea for me, who is not a gamer, but for gamers is quite common. And actually, I remember having this conversation with the game designers, with the game programmers, when we proposed using social engagement as a game mechanic. Their first reaction was like, no, you can't do that. You can't use social engagement as game mechanic. And I was like, why can't we? Why can you go into a game and shoot people and kill people and use that as mechanic, but not trying to be socially engaged with them, right? So I think we won the argument at the time, but it was a really interesting discussion to have them. So I think the method we use forces player to try to engage with the character in a socially meaningful way. And hopefully there'll be more new generations of games that will really look at how do we use game to strengthen social connections and really make the future of game more pro-social. Okay, so I think that's the kind of summary of that game. Just to wrap up, this again is my work is really about using the power of VR to improve how we socially connect and communicate with each other. And because I think it's important to actually have some quality in our social life, right? So it's not just said by me. It's there is a ongoing study which has lasted for about 80 years in Harvard, that they found that a strong relationship to be far and away the strongest predictor of life satisfaction and better predictors of long and happy lives than social class, wealth, fame, IQ, or even genetics, right? So it is social interaction is such an essential part of our life, and having quality social interaction is such an important part of actually having a fulfilling, satisfying life. So I just think it's just really important, and I really do see VR as a way to improve how we socially engage with each other. And just to finalize my talk, so this is a monster, but basically this is how computers see us, right? I mean, we normally interact with the digital world on a flat screen. So you have one eye, and normally have stereo audio. So you have two ears, and you just need one finger to click the like button or make a purchase. But this is not who we are. This is who we are, right? This is a homunculus, sensory homunculus. There's a motor homunculus, which looks very similar. So basically, it's proportion to the brain representation of different body parts we have, right? So this is kind of more close to who we are, and I think a lot of because we spend so much time now, interacting with the digital world. Even lots of our social interaction actually happens through the digital interface, and I felt actually what's going on is like society or the technology is trying to squeeze this monster on the right hand side into the monster on the left hand side, right? And I think that could be a quite painful process for everyone, and that's why we see an increase, in depression, in lots of mental health issues, right? And I feel like virtual reality could be a way to kind of break this problem, right? Because in VR, we're not only just using one finger to interact, we're actually using our whole body. And as you can see, the device conveniently sits on the three parts that really are highly represented in our brain, right? Our face and our hands. These are where sort of the interface of VR we're currently using. So I think, and the new generation of devices, as you all know, also tracks facial expression in real time, right? So we can, really have expressive avatars very soon. And I feel that should be an important part of how we interact and engage with the digital world. So in our lab, we're also, this is an example of work we did last year in IEEE VR, just comparing different type of avatars we could use. And how that contributes to the level of embodiment. But you can see real-time facial expression inside VR is there. In 5 years' time, I believe will be everywhere. I think in some social VR platform, it's already an integrated part of it. But it's not. It's actually quite a sort of tedious process. It's not easy to really get your facial expression right. But hopefully, as machine vision algorithms improve, we're going to see better and better integrations in that front. And we have also been doing some work on the hands, how we perceive haptics, because haptics is also a very, very important part of how we interact with reality. At the moment, you have a bit of vibration feedback from VR, but that's not enough. And I hope to see sort of more interesting haptic devices out there. And this is some work we've done, try to understand the cognitive load, the difference in cognitive load when using controllers and hand interaction, because I feel being able to see the hand representation inside VR is actually a very important aspect as well. And we run a master's degree at Goldsmiths, both MA and MSc in virtual and augmented reality. So if you're interested, to get in touch. And this is what our students have been doing. So we do a bit of AR work as well. And this is what our students are able to create after 2 weeks of studying with us. And I just want to say our students basically come from either a creative background or technical background, but they really learn from each other. So I think the future of this area is a very sort of collaborative area. So we need people who have both technical skills and able to be creative as well. It's really, really important to have both skills to push the future of this. And this is my lab. I run it together with Professor Marco Kilos. We have about 10 people, all basically contributing to the kind of social, empathic, and embodied VR research agenda we have. And we have lots of collaborators, lots of universities, companies, and creative partners as well. And we do enjoy meeting with each other in real life. Thank you. I think that's all I